So this is continuing on with different types of amino acids. We just finished talking about the hydrophobic amino acids in nonpolar group, and we're about to move on to the polar neutral amino acids. And if you look at these amino acids, notice that all of these have some kind of atoms that could hydrogen bond. So look at the OH here. So a lot of these are alcohols, like here and here, or amide bonds, as you can see here. And here's another alcohol. So 3 of them are alcohols, 2 of them are amides. So as the name indicates, they are neutral compounds. They don't have charges on them, but they're polar because they have polar side chains, such as alcohols and amides present. So a lot of these can hydrogen bond. Sorry. Which gives a different property when they're used as part of the protein. All right. Cysteine is a special amino acid because it's got a thiol side chain, and what happens to the cysteine is if it's part of a long protein, and let's say the side chain is coming off of that, and let's say we have another or it doesn't even have to be another protein. It could even be a same chain, and let's say there's another cysteine residue at a different end of a protein. What this does is that the thiol compounds, thiol can be oxidized with an enzyme, and it makes a di thiol, so it will link in a covalent bond. So it has a CH2S and then CH2S. It will form this bond, covalent bond between the dithiols, and that means that by forming this covalent bond, the protein chain that used to be just one long chain now is sort of stuck in a cyclic form, as you can see. And if there's an enzyme present to cleave that, then you go back to the dithiol form. So because of this possibility to make covalent disulfide bonds, cysteines are very important. And as you can see, a linear protein now becomes a circular protein, so it changes the shape a lot. And in fact, this chemistry right here is what is used when you go for perm. You have existing, you're born with some natural amount of cysteine in your hair, and by genetics is either straight or curly. But then what you're doing when you go get a perm is you are taking the pre-existing either the disulfide bond and breaking it, or you're taking the dithiol and then oxidizing it to form new bonds. So you are taking what exists naturally, changing it chemically by forming these disulfide bonds, and then the hair then is no longer in a natural shape, but is in a new shape, right? So how you classify what goes into the polar neutral, take a look at the side chain and ask yourself, is there a polar functional group present? And if the answer is yes, then it belongs to this category. The other two categories are very easy to tell because one is polar acidic amino acid, and notice the side chain itself has the carboxylic acid. So on top of the normal acid that is present in amino acid, you have an extra carboxylic acid in this aspartic and glutamic acid, as you can see. and that's why they're polar and they're acidic. The last category is the polar basic amino acids, and as you can see, they're extra amines in this category on top of the amine group of the amino acid, right? Notice in this one, you have two nitrogens, and as you might recall from your aromatic chemistry, in order for a ring to be aromatic, it has to obey that 4n+2 rule. And in order for it to do that, because this only has 4 pi electrons, one of the lone pair electrons has to participate into the ring in order to be aromatic, in which this ring is. So one of the nitrogen lone pair, it participates in that, and the other lone pair are available to act as a base. So that's why in this case, this ring is classified under polar basic, whereas tryptophan, in which you do have an extra nitrogen, so you might be tempted to classify this under polar basic amino acids, but in fact this lone pair, because there's only one nitrogen in the ring, is participating in this pi electron system in order for that ring to be aromatic, so it's really not available to act as a base to go grab a proton, so it's not basic. So that's the difference. So you have to keep that in mind for the histidine and tryptophan, why one is basic and one is not. All right. So once again, to summarize, you have in amino acids, you have an amino group or carboxylic acid group, and you have a side chain. There are 20 amino acids that you're responsible for in being able to draw, given the side chain. And I expect you to be able to draw with the correct chiral center. And I also expect you to be able to, given the R group, be able to categorize in nonpolar or polar neutral or polar acidic or polar basic amino acids. Okay? Now, once you become familiar with the type of amino acids is available, and I guess a side note to the characteristics of these polar acidic or basic amino acids is that they're going to be opposite of the non-polar amino acids. In other words, they're not going to be hydrophobic, but these are going to be hydrophilic, because these polar amino and polar carboxylic acid are going to like being next to water. So you find these polar amino acids on the outside surface of the proteins, and because they don't mind interacting with water, and that should kind of make common sense to you at this point. All right, so how do these amino acids exist in water? Okay, all these have drawn with amino group and carboxylic acid group. But do they exist like that, or do they exist in different form? Okay, so you've already come across the amino functional group, and you've come across the carboxylic acid functional group. And what is your first thought when I ask you what is the property of carboxylic acid? All right, what should jump into your head is that carboxylic acids are acidic, and we went over this over and over and over again. Okay. So that this proton is acidic, in other words, is easily given up because the O- that you create is stabilized by resonance and is shared equally between the two oxygens, right? So we know that the carboxylic acid is acidic. The other functional group, the amine group, what property jumps into your head when we talk about amines? Amines, as you know, are basic. So the lone pair on the nitrogen is able to grab an acidic proton. So obviously when a basic functional group and an acidic functional group exist side by side, only one carbon away, they're not going to stay that way, but they are going to do an acid-base chemistry. All right. So it turns out that amino acids in water don't exist in this form, but exist in a dipolar ion, as you see on the next page. I'm going to just focus on the different forms. And this should make sense to you because the acidic proton has been deprotonated, and it's the amine that's basic has gotten it. So it's an overall neutral species, even though it's got the two charges. And these kind of species that are that has both plus and a negative charge in a one molecule, and they're neutral overall, are called Zwitter ion. And you've seen other ions like this before. So in a physiological pH, which is pH of 7.3, a lot of the amino acids exist in this form, where it's overall neutral species. All right, because it has both the negative charge and the plus charge in one molecule, it's going to have dual properties, right? It's amphoteric in nature. What do I mean by that is that depending on what condition it sits in terms of the pH, it's gonna exist in a different form. Okay, so the pH that at which the amino acid exists in a neutral species is called isoelectric point, and this is abbreviated as a PI of that amino acid, and each amino acid has a different PI, and your book shows you how the PI is calculated. So it takes, for most amino acids, it looks at the pKa of the carboxylic acid, and it looks at the pKa of the amine, and then it takes the average of the two, and that's how they derive at the number for PI. So each amino acid having different PI, you could sort of think of it as like its property, like a melting point is its property. And by the way, because it's charged species, amino acids readily dissolve in water, is an ionic species, so that should make sense. It does not dissolve in organic solvents. It acts like a salt. In other words, they have a very high melting point as well. All right. So I'm going to run out of time soon, so I'm going to continue this discussion about what form it's in, depending on what condition it's sitting in the next lecture.